So moving forward with our trig unit, we are going to start to work with identities. I dare call them trig proofs, but that's basically where we're going. A lot of this is kind of like puzzle pieces. It's just trying to find equal parts. We're doing a lot of substitution, replacement ideas. So we need to know some basic identities, reciprocal identities. So think 1 over. Cosecants, reciprocal identity is 1 over sine theta. Secant's reciprocal, 1 over cosine theta. Cotangent, 1 over tangent theta. And now when we get to sines, now we think reciprocal of sine is 1 over cosecant. Cosine is 1 over secant. And tangent is 1 over cotangent. So these are all equal identities that we can use as we're trying to simplify some trig statements. Quotient identities, quotient meaning division. So we have sine theta divided by cosine theta. Reciprocal of tangent is cotangent, so the reciprocal of that quotient identity would be the cotangent identity. Okay. And some Pythagorean identities that we are going to be taking a look at. So Pythagorean identities, think a squared plus b squared equals c squared. And if we were to think about this on, let's say, a unit circle or wherever we were deciding to place a triangle, it does not really matter the quadrant that you put it in. So let's say, for instance, I put this down here. We always know, let's say, if I were to pick any kind of coordinate, it would go cosine comma sine, meaning that x length is a value of cosine and the y length is a value of sine. So if we were to think about this in terms of a right triangle, I could say cosine squared plus sine squared equals 1 squared. That's your Pythagorean identity, basic Pythagorean identity. Now, we can create two other identities that involve tangent and secant, and cotangent and cosecant, by just doing a little bit of algebra. So if we start with this identity, cosine t squared plus sine t squared equals 1, and divide through by cosine of t squared. And so if you do it to 1, you got to do it to everything. And then we reduce. So cosine squared divided by cosine squared gives us 1. Sine squared divided by cosine squared, that gives us tangent squared. And then 1 divided by cosine squared, that's a reciprocal identity, that's going to give us secant squared. So what we just did is produced a new Pythagorean identity. Okay? We can do the same thing, so we're going to start same basic Pythagorean identity, cosine squared plus sine squared equals 1, but this time we're going to divide through by sine squared. So again, divide everything through by sine squared, and then we're going to think, what identities do we have that when I reduce, this will simplify to a new Pythagorean identity. So cosine squared divided by sine squared, that's going to get us cotangent squared. Sine squared over sine squared is 1. And over here, 1 over sine squared is going to get us cosecant squared. So it's kind of nice as long as you know that basic one. If you forget these other two, you can always develop them by just thinking divide through once by cosine, divide through twice by sine, and now you get your new Pythagorean identities. So keeping those in mind, we're going to use those identities. Now we've solved this problem before with triangles, but we're going to use those identities to find sine of theta and cosine of theta if tangent of theta is 5 and cosine of theta is positive. Now, first thing, tangent of theta is positive. So when we're thinking all students take calculus, that means tangent could be in either quadrant 1 or 3. And if cosine is positive, that means it could be in either quadrant 1 or 4. So that means when we're looking at these answers, I want to think everything's going to be located in that first quadrant, meaning positive. Okay. Now we also have tangent. So I have to think of Pythagorean identity that goes with that. That's our secant one. So we have secant squared theta is equal to 1 plus tangent squared theta. And we're going to substitute that in. So I have secant squared theta is equal to 1 plus, well, if I know tangent is 5, I would have 5 squared. Okay, so simplifying, 5 squared is 25, plus 1, I get 26. And I just want to find secant, meaning I have to square root it. So now I have secant of theta is equal to, so now it could be either positive or negative square root of 26. But because we know it's located in quadrant 1, everything is positive in quadrant 1, so that means secant is just going to be a positive square root of 26. Now, if secant is that, I know that cosine is the reciprocal of secant. So I could tell you cosine of theta must be 1 over the square root of 26, since they are reciprocal functions, reciprocal identities. Now we have to find sine. So I could go back to that idea that I know what tangent is using those quotient identities. I know tangent is equal to sine over cosine. And since we know tangent is 5, I don't know sine, so I'm trying to find sine of theta. I know cosine right now is 1 over the square root of 26. And if I were to solve, think cross multiply, also think with fractions, tops of tops, bottoms of bottoms, that's going to show you that sine of theta is going to be 5 over the square root of 26. Now, you could do this with reference triangles, but you can also do this with identities. So it's just a different way of solving for missing parts of triangles. Okay, moving on with our identity idea, we're going to get into some things called co-function identities. Co-function is coming from the idea of co standing for complement. And if I'm thinking complement or complementary angles, I'm thinking I know that they're going to add up to be 90. So in a right triangle, if I know C is the right angle and I'm looking at these other two angles, I know that A plus B should equal 90. Those are complementary angles. And if we were to just take a look at A, starting at A, and just, if I were to label this, let's just go X, Y, and R, kind of thinking of the unit circle, and just write out the ratios. So I know sine of A, opposite over hypotenuse. And cosine of A is adjacent over hypotenuse. And tangent of A is opposite over adjacent. And now we can find all our reciprocals by just basically flipping them. So cotangent is x over y. Secant being the reciprocal of cosine is going to be r over x. And cosecant being the reciprocal of sine is going to be r over y. Now when we switch this up and we go to B, keep in mind your reference angle is changing, so adjacent opposite switch. So sine of B, this time your opposite's x and the hypotenuse is still r. Cosine, we have adjacent over hypotenuse. And tangent, now we have opposite over adjacent. So again, we can make all of our other ratios by thinking reciprocal. So I have y over x for cotangent. For secant, it's the reciprocal of cosine, so r over y. And cosecant's the reciprocal of sine, so r over x. Okay, so why do we go through all of this? Well, let's take notice of a couple of things here. Sine of A and cosine of B. So first off, A and B I know are complementary angles. I also am seeing that these two things are going to have the same exact value. So these are co-function identities. I can say the sine of one angle is equal to the cosine of its complement. Same thing here if I look at these two. Sine of an angle is equal to the cosine of its complement. Okay, if I look at cotangent and tangent, I can see the same kind of an identity happening. So doing all of this, thinking of our co-function, we get these co-function identities. So try and interpret what this is saying. Pi over 2, so that's 90. 90 minus an angle is equal to theta, the angle. So if I did 90 minus, let's just even play with numbers. 90 minus 30, well, 90 minus 30 is 60, should be equal to the cosine of 30. Well, 60 and 30 are complementary angles, and we just saw up there the sine of one angle is equal to the cosine of its complement. So these are co-function identities. These are identities, again, they're going to help us with some different proof kind of concepts or solving different identities that we're going to go see next. Then we get some odd and even identities. So maybe a quick review. Odd, we're thinking, if I'm thinking visually, this is symmetric to the origin, meaning flip it upside down, it looks the same thing right side up and upside down. And even being symmetric to the y-axis. Okay. And then we hit tests. So if I had my even test, we said the way I knew a function was even is if I could show the original function was the same as when I negated the x value. And to show a function is odd, that would be saying if I negated the x value, it's equal to when the function itself is negated. So keeping that in mind, looking at these odd and even identities, I can take a look at these functions and I know visually sine should be an odd graph. I'm just going to put O for odd. And so sine is having this odd idea where if I negate an x value, it's the same as negating the function. So its reciprocal identity is the same thing. It's also going to be odd. Okay, notice cosine's different. Cosine is following that even concept. So its reciprocal identity is also even. Tangent is following now again that odd concept, and so its reciprocal identity would be odd. Okay. So using both our co-function identities and our odd and even identities, we're going to see how this works. So it says sine of theta is equal to 0.45. We have to find cosine of pi over 2 minus theta. Okay, so this is a co-function identity. And I know that cosine of pi over 2 minus theta is equal to sine of theta. That's that whole idea of sine of an angle is equal to the cosine of its complement. So if I know sine is equal to 0.45, well, then I know cosine of pi over 2 minus theta also has to be equal to 0.45. And so you're done. Now, number 3 is a little bit more difficult because we have a couple of things working here, both the odd and even identities and our co-function identities. So if I'm looking at this first one, notice the values are flipped around. It's saying the angle minus 90, so it's like a negated angle here. So here's where that odd and even identity is coming in. So I could say sine of my angle minus 90, it's like the negated angle, should be the same thing really as if I negated sine of pi over 2 minus theta. So if I think about this, if I look up on top, this is what we just did here, that's using that odd identity. Saying sine of an angle is equal to if I negated sine. Okay, I have to find cosine of negative theta. Well, cosine of negative theta is equal to cosine of theta. So what we just have here, this is just identifying our even identity or even property of cosine. And if I plug them in, now think about this. We know sine of pi over 2 minus theta is equal to cosine of theta, but we don't have pi over 2 minus theta. Okay, what we have is theta minus pi over 2, but using this identity, I get this over here, sine of pi over 2 minus theta, but it's negated. All right, well, if I negate sine of pi over 2 minus theta, then I'm probably going to have to negate cosine of theta. Okay, so sine of pi over 2 minus theta, well, that's really, remember, equal to this, which is equal to 0.73. But I had to negate it, so I have to negate this. Okay, so what do we know? Well, we know cosine of theta is equal to negative cosine of theta. That's what we're trying to find here. But the only difference here is that I have it negative. So I know negative 0.73 is equal to our negative cosine theta, which would bring us right back to the idea that we're trying to find cosine of negative theta, and those would have to be equal. A little bit more challenging. Okay, and so here we're going to simplify some trig expressions. So this is kind of using some basic algebra, trying to think factor, divide, simplify. So we have this expression and it wants us to simplify it. So noticing what we have here, I have sine cubed and I have sine. In both terms, I have a factor of sine, meaning I could factor out sine. And then I want to see, well, what's left? Okay, well, sine times sine squared would get me sine cubed. And over here, sine times cosine squared would get me the second term. And now I'm noticing something. That looks like that Pythagorean identity, which that equals 1. So this whole thing actually just drops out. That whole expression that looks crazy complicated to begin with, we're just left with sine of x. Okay, so that's using some identities. That's kind of the proof idea that we're talking about. On the back page, we want to simplify this. So I want to think distribute through. And I see that when I multiply these, they're the same terms, but the middle signs are switched. That means once I do that distribution, that middle term drops out. So we get secant squared of x minus 1 on the top. And I'm going to divide that by sine squared x. Now, if I think back to those identities that we had an identity that said 1 plus tangent squared is equal to secant squared. This looks really similar over here. It's just I have secant squared minus 1. Okay, so let's move this around and say, well, what do I know that secant squared minus 1 is equal to? And it's equal to tangent. Oops, daisies. So over here on top, I could tell you our numerator is actually equal to tangent. So now I really have tangent squared of x over sine squared x. But we're going to simplify this more, because we know tangent squared is really sine squared over cosine squared if I use our quotient identities. Now I have a fraction divided by a fraction, so I want to think copy, change, flip. Copy, change my middle term, and then flip. And we're able to reduce diagonally. So this is leaving us 1 over cosine squared. And using those reciprocal identities, I can tell you 1 over cosine squared is really secant squared x. So again, we're taking something that looks crazy horrible and turning it into one term. Okay, and our last one. So taking it a step further by saying we have to find all of these values that solve this. In other words, we're going to factor, but now we're going to solve. So this works just like it did in Algebra 2. I want to get all of my terms onto one side of the equation, set it equal to 0, and factor. So I'm going to pull tangent over. So I'm subtracting tangent, setting it equal to 0. And I can see each of my terms have a factor of tangent of x. So I'm going to pull out that tangent of x, and I'm left with sine squared x minus 1. So just doing a little factoring. Okay. So now we're going to set each of these equal to 0. So I have tangent of x equals 0. And I have sine squared x minus 1 equals 0. Now I have to solve these. So I have to think, where does tangent of x actually equal 0? Well, tangent, remember, is sine over cosine. So I need sine over cosine to equal 0. Our coordinates go, if I think of this one, here's my coordinate 1, 0. Our coordinates are always going cosine comma sine. So if I do sine divided by cosine, if I do 0 divided by 1, I get a 0. So that means tangent of x equals 0 right here. And what if I took its negative, right? So negative 1 over 0. If I do 0 divided by negative 1, I still get a 0. So our solutions to this, I could tell you, would be at the location 0 and pi. So I get 2 answers there. Okay. Over here, set this equal to 0. And I would get sine squared x equals 1. Now I need to square root this. Keep in mind, when you square root, you get both a positive 1 and a negative 1. So now I have to figure out where is sine positive and negative 1. All right, well, sine is your y coordinate. So I need my y coordinates to be 1. So I have 2 locations. Here's my positive 1 at pi over 2. And here's my negative 1 at 3 pi over 2. So it looks like we get 2 more answers. But if we think about this, go back up to our original statement, I need to plug in tangent of pi over 2 and have this work. But tangent of pi over 2 is undefined. And same thing if I think about tangent of 3 pi over 2, it's also undefined. I have asymptotes at those locations. So what this really means is I have to reject both of these answers. My only answer to this solution is 0 and pi. I know that's a lot. I know that that's heavy. We're going to practice a lot of this in class. This is just the foundation to get you used to this. Hopefully we have an idea. We're going to start in class with practicing a lot of these, practicing our factoring and making sure our algebra is really strong. Okay, so don't get nervous. We're going to do this, and don't get worried that I called these proofs. They're not bad. Okay, have a great day.